So the first thing is atomic radius and ionic radius. And we're immediately going to go to a whiteboard. We have a periodic table here, and basically the atomic radius, if we draw out an atom, a basic atom, we have like the nucleus in the center right here. And then we have, let's say, the orbitals right here, looking something like that. If I could draw, obviously this isn't going to be even, but you know. And basically, if this were correctly centered, if I were a good artist, we'd have this distance right here, this atomic radius, that would be, this distance right here would be the atomic radius. Pretty straightforward, right? Obviously, this is not a, this is obviously not all in one plane, like how it's being projected, but it's obviously a sphere. A sphere has a radius, so does a circle, but we're talking about a sphere in this context. And an ionic radius in this case would be a, let's talk about Na versus Na plus, sodium versus a sodium plus ion. Sodium plus would just be sodium with one electron pulled away, right? So it would have a smaller radius because the electrons would be pushed less and less. And we're going to demonstrate that a little bit, actually. So we're going to go back to this atom, and we're going to draw some electrons on here. So obviously this isn't going to be right. We'll pick, I don't know, just some random atom with some random amount of electrons that I'm honestly not quite sure represents. We'll go with carbon, actually. So I think this is carbon. So in terms of the size of this thing, there's going to be two, check the chat real quick. There's going to be two factors that are determining the size of the carbon. We're going to go into a little bit of the physics here. When we talk about the electric force on something, I'm using my finger here right now. That's why you see my thing extending into the screen. We have this equation. The electric force is equal to a constant times the charge on that one particle, the charge on the second particle divided by the distance between them squared. That's what R means. So when we're talking about the size of an atom, let's say, there's going to be two factors here. But before I continue, actually, this technically isn't 100% right, because when we get to like the really small atomic scale, classical physics doesn't work anymore, like F equals ma and all that good stuff. An object in motion stays in motion. Once we get to the atomic scale, there's some weird probability stuff that happens, and it's not deterministic like it was before. Like I can't, if I fire a ball or if I kick a ball off a cliff, I can tell you the exact place is going to land away from that cliff if I know how much speed and what angle I kick it with. But in the case of like a small atomic scale, there's a probability distribution there, so it's not deterministic anymore. I can tell you like what the probability something will land in a certain spot is in that same scenario, but I can't tell you with 100% certainty where it will land. So this is an approximation, or rather, it's a way to develop intuition for this. So when we're looking at this, for example, carbon, when we look at the distance, let's say, between this proton or this nucleus and this electron right here, obviously the force is going to be attractive, right? Because negatives and positives will attract each other, opposites attract. Yeah, Coulomb's law. Yeah. But there's really no there's no interference here with other electrons, right? So when we look at the attraction between this proton or this nucleus and this electron, there's another electron right here, right? And based off the equation here, do you guys think this electron will have a stronger force, or the electron between the two will have a stronger force, or do you think the interaction between the nucleus and the electron will be stronger? So to clarify, I'm asking which attraction is stronger, or which attraction or repulsion is stronger, like which force is stronger, the force between the two electrons or the force between the outer electron and the nucleus? Yeah, so it's between the two electrons. I'm not sure which one I said first, but It's between the two electrons. And the reason why is because these electrons are very much like their distance is lesser in magnitude than the difference in charge. And what I mean by that, or I'll talk about this rather, when we look at the graph of like, dang, I'm going to just draw this out with my finger. When we look at the graph, we'll label this y, x. Let's say we increase the charge. If we have two charged particles right here and we increase the charge on one of them and we make a graph of how we increase it, it's going to look like a linear graph, right? Because this is essentially, if the distance is constant, this would be f, we'll say we're changing Q2. This would be y equals mx plus b. The b is 0, and this right here is just the slope, which is m. So the graph would look like this. However, I don't think. Oh, you're in clear mode. All right, I thought you were asking me. But if you look at the distance grows like a parabola, right? So if we take two charged particles, we keep the charge the same, and we move them closer and closer together, it's going to grow like y equals x squared because of the squared term in the radius. So it'll grow like that. And we could definitely easily see that the y equals x squared term is going to grow a lot faster than the y equals x term. So the distance matters a lot more than the charge. And what's happening here is when we look at this interaction here, the electron is going to be pushed away by this electron a decent amount more than it's going to be pushed into the nucleus by a different force. So the relevance this has to the periodic table is when we look at the atomic radius trend, the amount of electrons an atom has matters more than the amount of protons the atom has. So just by logic, the amount of protons will decrease down the table, right? I need to draw with my finger. This is not working. So the amount of protons will increase as you go down. And because the amount of protons will create a stronger electric force between the electrons and the protons, it would create a smaller atom because they're being held in more. So the atomic radius increases like that. So for example, or the atomic radius decreases like that. So this should be better actually. So for example, helium would be smaller than francium, and helium would be, or rather like boron would be smaller than aluminum because aluminum has a greater nuclear charge. Or rather, I'm going to rephrase that. So this is the biggest atom down here. This is a little impromptu, so I'm sorry if this is really confusing. This is the biggest atom down here, and this is the smallest atom up here. And the reason why is when you move down, right, you're actually increasing the number of electrons. So this right-left trend is going to be dependent on the number of protons because the most stable of each of these is going to have the same amount of electrons. So it's only dependent on the number of protons. And when we go back to this model right here, the number of electrons, when there's more electrons around the electron we're talking about, the outer electron that determines the radius, there's going to be a greater, it's called the shielding effect, because there's electrons around it that are repelling it, and when they repel it, it pushes away, so it creates a larger radius. So as the number or amount of electrons decreases, the atom goes like this. So this trend is essentially saying francium is the biggest atom and helium is the smallest atom. And this is actually hydrogen because we move hydrogen above helium in this case. So that's that trend. So what this is saying is what I just described, the classical principles are not accurate. Quantum mechanics and like a lot of math are the most accurate way to describe the atomic radius. And like even if you do try to describe the atomic radius with simple math, you can only describe it like exactly with hydrogen, just because anything past the 1 proton 1 electron case is too complicated. So now electronegativity, and electron affinity is next. And electron affinity is a measure of the tendency for an atom to attract a bonding pair of electrons. And if you recall, reactions are simply rearrangement of atoms via bonding pairing electrons, and they're usually between 0.7 and 4.0. For example, the electronegativity of hydrogen is 2.2, the electronegativity of calcium is 1.0, and electronegativity is undefined for the noble gases, which are the elements on the far right side of the table, because they don't react generally. If you want to be that one smart kid in your chem class and say, like, xenon can react with fluorine, then you can do that, but generally it's not reactive. And electronegativity trend is increasing with the red arrows. However, the row or the column with helium, they're unreactive, so there's no electronegativity, because electronegativity is a measure of how reactive something is. So it hasn't, all those have an electronegativity that's undefined. You could call it 0, but that implies sort of that there is an electronegativity, because you're not defining how you measure the scale. So for example, your scale could be like 4, or the electronegativity of fluorine plus some constant. And if you're calling the electronegativity 0, the real electronegativity would be that whatever that constant is. And obviously that's not a thing. So it's just undefined. And the reason why is because atoms closer to the noble gases require less electrons to fully fulfill their entire valence shell. So, for example, fluorine and all the elements below it will, every atom is trying to get an octet. It's in its most stable state when it has 8 electrons in its outer shell. And for example, fluorine, all fluorine needs to do is put one more electron in its outer valence shell to get an octet. So it takes the least amount of energy in that left-right trend to fully fill its valence shell. And carbon, for example, also needs to fulfill its valence shell, but it's not going to be as reactive because it's not as close to getting to its valence shell as something like fluorine is. So that's just the left-right trend. And what about the up-down trend? So atoms towards the top of the periodic table are, they're not larger. Why did I put larger? So less bonding happens because bonding occurs further from the nucleus. That should be because they're smaller. So something that's to the top of it will have, it'll react more. So the atoms going up are more electronegative because the atoms are smaller. So that's just a mistake in the size. I really should have looked that over. So when we're talking about, let's say, a carbon atom, a carbon ion reacting with an oxygen ion, the thing here depends on the distance between, roughly depends on the distance between the carbon proton, or the carbon excess positive charge, and the electron on the outer shell of the oxygen. And as you can see, if that distance were smaller, the force between them would be greater, so it would react quicker. So that's basically what that is. And for example, bromine has a electronegativity of 3.0, fluorine has electronegativity of 4.0. And electronegativity is a pretty simple concept, I think. If you have trouble with it, just ask questions in the chat, really, or there's plenty of resources online, just because chem is such like a unified subject, especially, college level chem. So as you can see, let's say if carbon was a larger atom, or if this carbon anion was released with, or this carbon had a greater radius, it would require, or there'd be less force between the outer electron on the oxygen and the nucleus of that atom. So the reaction would be less reactive. That'll be better defined when we go to kinetics and reaction rates, but for now, that's just going to have to suffice. So next is ionization energy, which is what you were talking about earlier in the questions. So ionization energy is the energy required to remove an electron from an atom. Here we have a general reaction. So this is an atom A with charge N, and it ionizing would be it losing an electron and it gaining a +1 charge. So for example, a neutral hydrogen atom ionizing would produce a hydrogen ion with a +1 charge and an electron. And in this case, this example is literally just ripping apart a proton and an electron, nothing more than that. And you can have the first ionization energy, which would be that first reaction, the second one with the second reaction. And obviously for something like hydrogen, neutral hydrogen only has 1 electron, so you obviously can't have a second ionization energy. But for something like that, you would only include the first ionization energy. And the ionization energy trend is increasing with the red arrows for a really simple reason that we'll do when we go back to the drawing board. So keep on forgetting that I have to actually share the tab. Share screen, application window, table. Okay, so as we know from previous slides, the atomic radius trend, it gets smaller as you go like that. And it's really simple, honestly. An atom requires more energy to ionize to remove an electron if the atom is smaller, because there's less distance between the outer electron and the nucleus. So the nucleus is holding it in more effectively than it would be normally. So for example, a helium atom would have a pretty short distance between the outer electron and the nucleus. However, francium, or we'll talk about cesium rather, because the radius of francium is kind of experimentally undefined. But cesium, for example, would take more energy. Now, when we're talking about first ionization energy, that's obvious. When we talk about second ionization energy, I'm going to ask the chat, do you guys think second ionization energy is greater than the first or lesser than? Just better than no answer. No, second ionization energy is greater than the first always. The third is greater than the second. The fourth is greater than the third. And the reason for this is because when you pull, let's say, this outer electron out, these electrons right here are experiencing less shielding from this electron. So when it's experiencing shielding, it's easier to pull out because it's being more repelled from the atom, right? That should make sense. But when we pull that electron away, there's less shielding on the other electrons. When there's less shielding, the attraction between the protons and the electron is greater. So it's harder to pull them out because the nucleus is pulling in the electron further. And that's pretty much it. And there's some more ideas with ionization energy, obviously, because this is AP. So we're going to have to go dive a little deeper into the concept. So you're going to need the periodic table. And the challenge is, which atom is this ionization energy table for and why? I'm giving you that it's in the third period. The ionization potential different than the actual ionization energy. What do you mean by ionization potential? If you mean like the potential energy associated with like the interaction between the electron and the nucleus, I imagine there's a slight difference, but it would follow the same trend. But I just imagine there's a slight difference because, like I said, like on the atomic scale, things aren't going to exist deterministically. So the position of that electron isn't exact. So like we obviously can't calculate its exact potential energy with the interaction. So yeah, second would still be larger for the same reason. It's just because we're like there's an uncertainty in the position doesn't mean that the position or the potential energy is like position independent. I hope that makes sense. Like for an electron, like we can know like its probability, like we can like say with like 90% certainty that the electron will be in this place. So like we can still apply this for that reason, but there's going to be slight deviations because we're not 100% certain that the distance between the nucleus and the electron is going to be this value. I don't expect you guys to be able to answer this question. I'm just putting this on here to demonstrate something. This is aluminum, and there's a very intricate reason why. And don't feel bad if this kind of stuff is difficult for you, just because this is like the hardest or one of the hardest topics for me for this class, like this exact thing, like determining an element based off of the ionization energy table, just because it's a very weird thing to think about. So I'm going to explain this. And the reason why it's aluminum, if we look at aluminum here, like I mentioned before, aluminum, or any element really, its goal is to have a full octet. Now, an atom won't always try to fulfill its octet, by gaining electrons. In this case, it would be losing electrons. So the quickest way to the noble gas part of the periodic table isn't to go the silicon, phosphorus, sulfur, chlorine route to argon. It's to go back and go to magnesium, sodium, and then loop all the way back and go to the neon position. So when we look at the ionization energy here, where do you guys see the biggest like jump between ionization energies? Just like, for example, like between the second and third, the third and fourth, the fourth and fifth, the fifth and sixth, etc. Yeah, so when we, yeah, so you guys are all right. It's third and fourth. So this jump is representative of pulling the electron away from an atom that's already fully stable, because it's going to take more electron, or it's going to take more energy to pull an electron from an atom if it's in its most stable state, because that's the strongest state that it's going to be in. So when we look at it here, I'll go, actually, no, I won't go back to the whiteboard, but from aluminum to magnesium, that would represent the first ionization energy. Obviously, the atom is staying the same, but when we're talking about electron configuration, we're changing aluminum's electron configuration to where magnesium would be. So from aluminum to magnesium, that would be 578 kilojoules per mole. From magnesium to sodium, that would be 1,820 kilojoules per mole. From sodium to neon, going backwards, essentially like if the periodic table was a tube, that would be 2,740 kilojoules per mole. And then once we're pulling away from neon, that's the largest jump in the change in kilojoules per mole and the change in terms of ionization energy, because it takes a way more amount or way more energy to pull an electron away from an atom in its most stable state. Does that make sense? Just doing a quick like conceptual check, just making sure I'm not going over anyone's head. Okay, that's good. So do you guys have periodic tables with you at all? If you don't, you could just pull one up on Google Images. Yeah, so just pull it up on Google Images, because this next question is it's the same kind of question. You're gonna need it. So the next one is, which atom is this ionization energy table for and why? I'm giving you that it's in the second period, so that's the second row. And why are there not values for the seventh and eighth ionization energies? So you need a periodic table to solve this. I'll give you guys a minute about. Again, if you have any questions, you can ask them whenever, especially while people are doing work and solving this problem. Remember, you're looking for the closest path to a noble gas, and that fourth and fifth jump should be representative of the ionization energy of something in a noble gas configuration on the periodic table. Hope you guys at least try to work it out. These problems are really hard to think about, so don't feel bad if you didn't have the time. The answer is carbon. And the reason here is because carbon, no, so the element would be in the second period, and magnesium is in the third period. So the reason why it'd be carbon here is because you can go either towards neon or away from neon when talking about the electron configuration for carbon here. If you're going towards neon, 1, 2, 3, 4. So pulling away the electron the fifth time would require the biggest jump in energy. And the same case goes backwards. 1, 2, 3, 4. Be like pulling an electron away from helium. And the reason why there's not a seventh and eighth ionization energy is because a neutral carbon atom only has 6 electrons, because it only has 6 protons. If it's neutral, there are only 6 electrons, because if it's neutral, the amount of electrons should equal the amount of protons, or it has to equal the amount of protons, actually. Does that make sense, guys? Again, quick check. There are pretty these kind of problems online. This kind of stuff is emphasized on AP, like thinking in terms of numbers, but not necessarily like calculating things is a big thing on AP, which is honestly kind of disappointing because chemistry is very computationally heavy in college, but can't have everything we want. So the next thing is density. And density is just mass per volume. Quick side note, density can be anything per volume. So like mass density is mass per volume. Charge density is charge per volume. Population density is population per volume. In this case, it would be, like square footage. So just knowing this definition, I'll ask you guys this. At 1.08 TM and 0 degrees Celsius, those are relevant numbers that are not needed for the problem. 1 kilogram of helium occupies 5,600 liters of space. What is the density of helium in grams per liter at this pressure and temperature? And the answer here is just mass per volume. So it's in terms of grams per liters. So you convert the kilograms to grams, which is 1,000 grams. 1 kilogram is 1,000 grams. And then you divide that by the volume because it's mass per volume, and you'll get 0.18 grams per liter. And density trend is kind of like the odd one out. I remember very famously my chem teacher, who's was considered to be one of the by far best teachers in the school. When he was teaching density, we asked, he literally prefaced it with I don't know. So density increases as you go diagonally into the periodic table. And the most dense element in this case is osmium, which is OS. So, osmium would be more dense than beryllium because it's closer to that part of the periodic table. So based off this, do you guys think oxygen or aluminum is more dense? Yeah, it's aluminum. That's not too difficult to come up with. So today's a short slide. So really what the goal here is, I think it's really hard to get this atomic trend stuff if you just kind of absorb information. So I really want you guys to ask questions or really anything at all, discuss in the chat. The diagonal density trend is more based on the volume because relative to other stuff, the mass between two elements is pretty invariant, right? If we think of the mass of my phone versus my computer, there's a big difference there. But if we're thinking of the mass of boron versus mercury, there's really not that much difference. So the thing is more based off volume. In that case, there's some complicated molecular geometry and volume of things, and some really, really difficult stuff, honestly. And a lot of these transition metals, you can't even describe their geometry with normal chemistry. You have to move past and learn inorganic chemistry, which typically students learn after 1 extra year of chemistry after general chemistry, or 2 extra years after general chemistry. So it's a really complicated thing. And I'm sure if you have the math background and can very easily visualize 3-dimensional shapes in your head, it would not be absurd for me to believe that there was some sort of explanation online. Personally, I don't have the background to explain it. And I don't even think density is on the AP exam just because it's so strange. Right. I tried to answer that question implicitly, but I didn't. And I also didn't really talk about electron affinity. Density plane defining the molar mass as a gas. So there's a very, I'll hold on, Dakota. I'll talk about this after this because we're just on the topic of density. So it's hard to differentiate between these things because density of an atom is different from density of a gas of the same molecule, right? Because oftentimes we don't even consider the volume of the atom itself, or even we never do actually. In the ideal gas law, one of the assumptions is we don't even consider the volume of the molecule. So the density of a macroscopic gas of all these atoms flying around at all these all these different speeds, the density is more based off of the average distance between the things, between the molecules, which is more based on the temperature than the actual properties of the molecule itself. So this density that I'm talking about, on a periodic trend, is more It's more like the average density of the molecule itself. But when we're talking about molar masses of like a gas, there is a formula. I think it's molar mass is density R constant temperature divided by pressure. But it's a different kind of density. It's describing a density that's based more on the interactions between the molecules themselves rather than the actual geometric like makeup of the molecule. And the atomic radius affects the ionization energy, because when we have a smaller atom, the electron is it's harder to pull away from the nucleus because the electron and the nucleus are closer together. So if two charges are closer together, they have more force between them, so they're harder to pull apart. And electron affinity, I did have electron affinity on here originally, but then I took it off because it's not really relevant. Yeah, you can ask whatever. Like I'm a physics major. This is kind of like questions like that are kind of my thing. Like I should definitely know this. But electron affinity, back to your question, Dakota. Electron affinity is the likelihood that a gas takes in an electron and becomes ionized, meaning like, let's say, like argon gas, for example. The noble gases can ionize. When they pull in an electron, they become ionized. So it would be argon with a +1 charge. And this specific case, the larger or the smaller an atom is, the more likely it is to pull in an electron. Just because if we think about the general shape of a molecule, when it's really small, the electron is really close to the proton. And when it's closer to the proton, the electron that it's about to ionize with can be both repelled by the electron and pulled in by the nucleus. However, the nucleus is a larger charge. So when that electron, that outer electron, and the proton are close together, the effect can sort of be canceled out by the larger or the higher charged nucleus. So the smaller an atom is, the more likely it is to pull in an electron. And the smaller an atom is, the harder it is to pull an electron away from it. Does that make sense? Okay, good. Anything else? I mean, we're just going to go into practice problems if we don't have anything else to talk about, or if we don't have any other questions. It'll essentially just be being like this atom versus this atom, which one will have a higher ionization energy? How many ionization energies would it take to like reach that jump that I was talking about earlier? Which one's smaller? Which one's bigger? All that stuff. No, you don't. I'm laughing because like I think it's like really stupid to test kids on like the history of science in a science class. It is important to know. Don't get me wrong, especially if you want to do science in college and do science as a job. It's really important to know the history, because if you know what other people did, it's a lot easier to follow their path and discover something new in the same fashion. But you guys are high schoolers. Like, it's really like dumb to test kids like for Regents Chem to do that kind of stuff. But it's not dumb learning. So I wouldn't be discouraged by learning the history of chemistry, but I would definitely advise you away from like spending all this time to learn the history of it, just because like, I mean, it's really not important in the big picture yet. It would be important if you were doing like chemistry research as like a PhD student, or like working in like a university in a chemistry department. But like, no, your answer is no. You don't need to, but I'd recommend it just because it's honestly cool. It's a great way to connect a subject to like us being people, right? Because like you discover, like you see a mathematical equation, like talking about something like complex, like really like a complicated, like convoluted concept, and you're like, that doesn't seem real. But like if you like read up on the history of like how that equation came to be and like all that good stuff, you know, it feels a little more real. It feels a little more personal, like another person did that, not that a computer just spit out an equation. So I answered that question more than I needed to, but I feel like that's an important thing to get out. If you guys are like doing other stuff in your units, like in your chemistry classes that isn't related to this stuff, you're free to ask me, like right now. This was all last year, so I may forget it or I may have forgotten it, but I can definitely point you in the right direction if I did. Because you were talking about gases, so I'm guessing you guys are on like gas topics, right? That's a fair assumption. I don't know. I'm gonna start asking you guys questions about the like relative sizes of an atom. Hope you guys are okay with that. So I'm gonna close the video again. Share screen, application window. So we're just going to be going off basic trends here. First question, do you guys think zinc or chlorine is a bigger atom? Zinc would be, I'll use my fingers again. Zinc would be right here, and then chlorine would be right here. Yeah, zinc's a bigger atom. It's just further down the trend. And for the same case, it has both more electrons and more protons. So it has two reasons to be a bigger atom. I'll ask you guys a bit of a trickier question. Do you guys think phosphorus or carbon is a bigger atom? Yeah, Claire, that's right. The reason why is because when we talked about the model first, right? You got a nucleus here and a really badly drawn orbital. That is one of the reasons. It's a bigger energy level, but that's I'm gonna try to move away from like energy level and like all that like quantum stuff and talk more like more on a macroscopic scale, or make macroscopic analogies rather. So when we're talking about, we'll put some electrons here, make another bad orbital because that's fun, right? So when we're talking about size of an electron or size of an atom, we're drawing carbon again. Do you guys remember which interaction contributed more, the electron-electron interaction or the electron-nucleus interaction? Yeah, electron-electron interaction. So when we compare these two atoms right here, these carbon and this phosphorus, there's two reasons to think that one of these is bigger. However, the trend here is when it goes down, when it's bigger, I think. No, when it goes sideways. Yeah. So the contributing factor here is when it goes sideways, it's bigger. And this is because when you go sideways, there's more and more electrons. So the sideways trend triumphs the up-down trend. If that makes sense. And this is just in a general case. Obviously, there's exceptions, but you're not going to really be asked about exceptions on AP. You're going to be asked more about the big picture. Does that make sense, guys? Awesome. Yeah, I mean, we're about 7 minutes out of time almost, or 7 minutes till we're out of time. Anything else, guys?